You might credit some modern technology to NASA, but have you ever wondered how that technology got from use in space exploration to you? And do you think you could go an entire day without using NASA technology? Next on the Rocket Range.
These are spacecraft that can keep on going forever and ever in space, and they will open up the resources of the solar system to humanity so we don't have just one planet anymore.
EGS Program Chief Engineer. Verify no constraints to launch.
EGS Chief Engineer team has no constraints.
I copy that. You are clear to launch.
5, 4, 3, 2, 1, and liftoff.
Power clear. Now passing through max Q, maximum dynamic pressure.
Welcome to space.
NASA has a reputation for creating history-changing technology, and much of that technology is available to you right now. One of our secrets to success is that we aren't developing all of this by ourselves. We're leveraging industry and students to make innovative leaps. This is done primarily through our Small Business Innovative Research and Small Business Technology Transfer Research programs. But before we get going, we want to make sure you know we'd love to hear your questions. We'll tackle one each show, and you might even inspire a whole episode. Tweet us using #RocketRange. Today, we're going to talk to Dr. Phil Metzger, who works for the University of Central Florida in partnership with NASA, about his World Is Not Enough robotic spacecraft. But first, we caught up with Mike Vinge, the Small Business Technology Manager at NASA's Kennedy Space Center, who helped us understand how the foundation of our collaborative programs work. All right, I am in the booth now with Mike Vinge. Mike, thanks for being here today.
Happy to be here.
So I want to start with this very broad question of, could I go a day without using NASA technology in America?
I don't think you could. I really don't. If you really make a strong effort to be kind of backpacking out in the woods, I think, yeah, you could maybe get there. But even then, you'd probably be surprised at the stuff that's inside your backpack or even the liner inside your jacket. It's probably got a lot to do with some of the materials work that we've done. A lot of people are familiar with the emergency blankets that you'll see people using. The Red Cross, for example, or ambulances will have the aluminum foil mylar blankets. If you think back to the Apollo program, that's actually the material that we put around the outside of the legs of the lunar lander to make sure that the temperature variations weren't something that would cause problems with the structure underneath. So we were literally developing this material to wrap it around the outside parts of our spacecraft, and that's the very same material that you see folded up in a little mylar blanket that people use for Red Cross.
How did it go from a lunar lander or some other NASA application to the department store or to your local convenience store?
I think a lot of times what is unique about NASA technology development is you're bringing together a diverse group of people who are looking at a problem in a fresh way. And it's that group of people who come a lot of times from different industries. As an example, the SBIR program, Small Business Innovation Research Program, we put out a solicitation that has about 90 to 100 different research problems that NASA has, and that's open for everybody across the country to answer if they're a small company. Now, what we get is a very interesting variety of responses from small businesses that are in industries that we might not have thought of originally to even talk to. But yet, the problems we describe in that type of solicitation ends up being similar to something that they've seen in their situation, and they know how to adapt it. And many times, there's that sort of incremental progress that can really make a big difference for technology development. For those who have been following the progress that we've had on the International Space Stations, a few years ago we had a really remarkable moment where, for the first time, humans grew their own crop in space and were able to eat that crop.
On August 10th, astronauts on the International Space Station sampled their first space-grown salad and pronounced it good. They were treated to freshly harvested red romaine lettuce grown in the veggie plant growth chamber, a special structure designed to make gardens flourish in weightlessness.
Which is awesome.
Yeah, that had never happened before. And one of the reasons that was possible several years ago was because the SBIR program helped fund the research for the development of something called the veggie, which was the growth chamber that the actual growth took place inside of. And that's something that took multiple years and a lot of work with different folks. But it was something that we relied on the innovation coming out of small businesses in order to accomplish. The systems that you would normally use to water a crop don't work as you would expect. Because if you think about it, when you're watering a crop, that's something that normally happens with earth gravity. And you can rely on the gravity to drag the water down to the roots who need the moisture.
In a weightless environment, there is no up and down, so roots grow in all directions. Water and substrate, the materials used to anchor these plants and allow for root growth, tend to float away. With veggie, these problems are solved by using plant pillows, bags of substrate with space dirt and controlled release fertilizer. Wicks are implanted in the bags to draw water into the substrate and provide a place to glue the seeds, which are oriented so roots will grow down into the substrate and shoots that emerge will push out of the bag.
And although we did have some prototype systems, we found out quickly that we were unfortunately having to ask the astronauts to help by manually watering some of the roots and stuff. And that ended up creating a need that we realized to have some sort of watering system that didn't rely on gravity.
Hi, Scott Kelly aboard the International Space Station. I want to go and check on my flowers I'm growing here in the Columbus module. It'd be kind of nice to have some flowers up here when you don't see much that is alive and growing besides the 6 of us here.
So there was an example of the type of technology call that went out, and so people across other agricultural industries who had never thought that they were going to have a need to talk or opportunity to talk to NASA suddenly found themselves to be right in the area of discussion. One interesting area in the past few years has been the fields of autonomy, as an example.
Sure.
We have found on the NASA side of autonomy, we have an interest in making sure that we have reliable systems that are rugged and can work unattended on other planets for some period of time. And that's the type of autonomy that we would have, is some sort of smart system that would be able to detect when there's maintenance problems or even perform its own maintenance and that sort of thing, and make it to where it's ready for human occupation at a later date or that sort of task.
So you mentioned autonomy being a good example. So essentially, we know that as we return to the moon, we're looking to do that with commercial companies. And so we're going to try and do a little upfront kickstarting of autonomy in commercial world, hoping that they will evolve further than the initial product so that we can glean from them and use them to help us get there effectively and efficiently.
It's even more terrestrial than that. Although the lunar example
sure,
is
yeah,
good.
Just an example.
But let's take for an example when we're talking about autonomy as it has to deal with processing of materials. The same type of autonomy that would be advantageous to NASA in terms of a robot driving a scoop of lunar dirt by itself, that same type of autonomy is also of use for a mining company that has an autonomous dump truck down in a tunnel 200 feet below the ground.
I did want to ask, so we heard about this project that we're going to find more out about wine. World is not enough. So can you kind of talk me through what's been the process for the wine project as they've kind of worked through the SBIR process?
Sure. This particular company, they were able to essentially produce a robotic rover, a robotic free flyer that can utilize the resources on the planetary bodies that it lands upon in order to get to the next location. That's about the best way to describe it.
Sounds cool, right? Now here's Dr. Phil Metzger to talk more about it. All right, I am here in the booth with Dr. Phil Metzger. Dr. Metzger, thanks for being here.
Hello, Josh. I'm glad to be here. Thanks.
Hey, so we are talking today about getting technology from NASA into the hands of the general public. And we do that obviously through different means. But I've been told you're working on a project called WINE, which is an acronym. The world is not enough. So I feel like we need So what is WINE? Where did we get the name World is Not Enough? Because obviously like that's a pretty powerful name.
We're at a critical point in our development as a species here on planet Earth. I think we've got a civilization that has outgrown the planet. And we see a lot of symptoms of that with the way that our civilization is affecting the climate, the way that we're depleting resources. And so in order for our civilization to keep moving forward, doing ever bigger and greater things, we need to stop relying on one planet for all of civilization's resources. I think it's time that we start putting the machinery of civilization off the planet and allow biology to have more living space here on this world. And we can do that. We know there are ways to start moving the machinery of industry off the world and yet support civilization here on the Earth, as well as doing greater things in space.
So you talk about we've depleted the Earth's resources. Now, are we talking like we're in a doomsday scenario here, or do we have time?
I do not believe we've actually depleted the resources on the Earth. What I'm talking about is we've used up the most easily accessible resources. It takes ever more energy to access and process the lower grade resources that are not depleted. And because of that, our industrial footprint it becomes ever greater. We need to process more energy, process more raw materials in order to produce the same outcome. And we also still need to make sure the whole world has a good economy and access to healthcare and education. And so we're not done industrializing yet all over the world. What I'm talking about is reducing the industrial footprint on the Earth by putting the machinery off the planet.
Okay.
The total resources have never left this world. They're still all here. And it's just a matter of energy to process everything. And the efficiency of that processing is getting less as we've used up a lot of the higher grade ore bodies.
So you're proposing this idea of going somewhere like the moon or Mars and bringing resources back here?
Well, it's a decades-long program, I think, but the real goal would be to eventually have power systems that are off the planet beaming clean energy down to the surface so we can move the entire energy sector off the planet and the entire industrial supply chain that supports the energy sector. We can also move the majority of computing off the planet. Right now, the energy needs of computing is growing exponentially, and at the current rate, according to the Semiconductor Research Corporation and the Semiconductor Industry Association, the computing here on planet Earth is going to require the world's entire energy supply by the mid-2040s. And
wait. So we're going to need all the energy of Earth to run computer servers by the 2040s.
Well,
an estimated figure.
It won't actually happen. What will happen is eventually there's going to be increased cost for the energy to supply what computing requires or desires. And so it's going to result in a reduction in the amount of computing we can do. And that's going to limit the benefits of computing. We won't be able to do as much supercomputing to solve for new drugs, figuring out how proteins fold. And there's going to be limitations to what we can do digitally unless we can move the computing off the planet. And there's a hope that we can improve the efficiency of computing, but even if we do, that's only going to even if we make the most optimally efficient computer, that's only going to delay the crunch another 10 years.
Sure.
So by the mid-2050s at the latest, we're going to have to either dramatically increase the energy supply of planet Earth or start to move computing off the planet. So I'm not looking at bringing physical resources back from the Earth. I'm looking at ways that we can create infrastructure off the planet in order to support life here on the planet using massless transport up and down.
So kind of a part of this, you mentioned a robot that never dies, because you're not proposing that this robot is going to solve all these world problems. But I'm curious to know, what does this robot that never dies do?
Okay, so it's actually a prospecting robot. So this is a spacecraft that could go out to any relatively low gravity object outside planet Earth. It could be asteroids, it could be the moon, it could be Europa or Titan or even Pluto. anywhere that's got low enough gravity and has access to volatiles like water at the surface.
So the technical definition of a volatile is a substance easily evaporated at normal temperatures. And so for our purposes, oftentimes that's thinking about cryogenic materials, things that we have to cool drastically in order to be a liquid, but at room temperature, they're a gas.
Right. And this robotic spacecraft mines the surface to extract the volatiles, and it converts it into steam, and then it can hop in the low gravity environment using steam propulsion. So it never runs out of rocket fuel as long as it's got an energy supply, which could be solar energy in the inner solar system, or it would have to probably be a nuclear decay source in the outer solar system. As long as it has energy and access to volatiles, it can just keep on exploring.
Can it ever get stuck? Like, is there ever a chance where this thing like hops into a hole or lands on a rock funny and tips over? Like, how do we know this isn't going to happen?
Well, it definitely can happen. And when we devised this project, our thinking was that we will send swarms of these out into space. They can be made very inexpensively using student teams, using off-the-shelf CubeSat hardware, 3D printing, the custom components. So this was designed to be built in massive quantities and sent out into space in swarms. The idea...
It sounds really creepy. You know that, right?
We will send swarms of these out into space.
Like these giant, like kilometer-long hopping robots. Like that sounds really creepy.
Hopping through the solar system like roaches. Yeah, well, so they would not be intelligent. They could not take over.
Okay, good. Whew.
Yeah, but they would. The idea is that some of them are going to land on asteroids that have water, and they're going to refuel, and then they're going to study that asteroid and send data back, and then they'll hop to another one. But other ones are going to hop onto an asteroid that doesn't have water, and they get stuck. So that's the end of their mission. So over time, they're going to end up stuck on asteroids, and that's fine. They'll still provide data about the dynamics of that asteroid as they radio back their location. But eventually, over time, the swarm will be thinned down.
Okay. And when you say a swarm, like, kind of give me a frame of reference. Are we talking like a dozen, 100, 1,000? What's the number look like?
It could be thousands because these are built with off-the-shelf hardware that's designed for CubeSat. So they could be very inexpensive, and they could be built by student teams as projects. They could be built even by community groups, people who want to participate in space. You could have a Boy Scout group build a satellite as one of their projects, and then it could go into space and participate as part of this swarm of spacecraft exploring the asteroid belt. Right now, we're sending on average one spacecraft to a small solar system body every 2 years. There are approximately 10 billion small solar system bodies. At the rate we're going, we will never explore them all until the end of the universe. But this would be a way to change that game, to send out large numbers of spacecraft and visit many, many, many of these small objects throughout this gigantic asteroid belt and then out into the Kuiper belt. So it'll give us a chance to really take survey of this home that we live in.
So how big of a robot are we talking about here?
It's the size of a microwave oven.
Okay.
In terms of CubeSats, it would be 27U. That's 27 units. It's 3 by 3 by 3 CubeSats.
So for those that aren't familiar, the CubeSat is a very growing trend of space-faring satellites, and they measure 10 centimeters cubed?
That's right, 10 centimeters on a side. Yep.
Okay.
And so the wine was just, and by the way, the CubeSats are modular, so they're made to be hooked together. And so you can have, quite often you'll see CubeSats that are 3U, and so those would be 10 by 10 by 30. And it's just 3 cubes hooked together. Okay. You often see them as 1 by 2 by 3, so that's a 6U.
Okay.
So what we're talking about is 27U. It's just 27 CubeSat-sized boxes hooked together, 3 of them on a side.
So we've got robots exploring around our solar system, and this would be on the much smaller side. Is that a fair assessment?
Yeah, this is definitely a small spacecraft. And part of the idea of the WINE project was to make use of the growing availability of CubeSat components. So we can use CubeSat reaction wheels, CubeSat communication systems, CubeSat power systems, and computers. However, we are not a CubeSat. So we are using CubeSat components and we're using CubeSat dimensions, but we don't actually have 27 modular units hooked together because the propellant tanks don't fit in just one unit.
Sure.
It's got legs attached to the side. It's got a nozzle sticking out the bottom. So it's not really entirely fitting the CubeSat philosophy, but it is leveraging CubeSat philosophy to a degree.
So give me kind of a feeling. We talked about kind of the energy that it has to do propulsion. We've talked about its size. So if we put this thing on Earth and you've got it working at full power, how far can this thing hop?
Well, here on Earth's gravity and in Earth's atmosphere, it's not going to perform very well. For one thing, the steam propulsion has a great advantage in space because as you're blowing steam out the rocket nozzle, there's a huge pressure difference from inside the upstream in the nozzle to outside the nozzle. And that pressure difference is enough that it causes the steam to go supersonic as it flows down the nozzle. But if you try to operate that inside of a dense atmosphere like on the Earth, you may not be below the critical pressure on the outside.
Okay.
And so you may not get supersonic flow. So it's going to dramatically reduce the ability of the propulsion system to create thrust. The second problem is the high gravity.
Sure.
So here on the Earth, I'm not sure you're going to get a very good hop at all. In a thin atmosphere like on Mars, it would definitely work. And you could hop hundreds of meters.
A single hop?
Yeah.
Hundreds of meters?
Yeah, that's true. That's correct.
Yeah, that's awesome.
Now, the metric I was using was to try to make it hop at least 1 kilometer per hop, and also to be able to heat the fuel, the steam, in 10 days or less. So you mine the water, and then you spend some time heating it. You're using solar power if you're in the inner solar system.
Okay.
So over a 10-day period of time, you're trickling in the solar energy and just building up temperature and pressure inside your water tank. And my objective was to make sure the spacecraft could get to hopping temperature within 10 days.
Okay.
So you could have a spacecraft, you could allow it to take longer than 10 days if you wanted to, but you have to draw the line somewhere for it to be a practical system. So if you could heat it up in 10 days with a sufficiently small set of solar arrays as your power source, then it becomes a very viable spacecraft according to our reckoning.
And so when we talk about that, obviously you have to not only account for the liftoff, so to speak, the hopping portion, but the touchdown portion. Do you save some of the steam to kind of slow your descent, or are the legs built so that they can withstand that force?
We were planning to do soft landings using the steam propulsion. So when I say it hops a kilometer or more, that means you're using about half of the steam for liftoff. You're using a little bit of the steam for attitude control using tiny thrusters. And so you're controlling the spacecraft using the same steam, and then it uses the other half of the steam to set down softly at its landing site.
Cool. That's amazing. And if you mentioned harvesting water, I'm assuming we're not talking about like streams of water here. We're talking about frozen water. Is that correct?
Yeah, well, it really depends where you are, what kind of a body you're on. So if you're on Europa, the whole surface is ice.
Okay.
And it's probably mixed composition ice. It can be water, carbon dioxide, it can have all kinds of organics. And for this spacecraft, it really doesn't matter. Whatever it gets, it can convert all of that to high pressure vapor and then shoot it out the nozzle and get propulsion. So we don't really care too much what the composition is. That's one of the nice things about this very simple system. If you're on the moon, then it's going to be ice mixed with dirt, mixed with mineral grains. And so the system has 2 coring tubes. It drives them down into the soil, and then it heats the coring tubes So the vapor will travel through the soil, up the coring tube, into a pipe, and into the tank where it gets frozen. Some of the vapor will leak out the bottom of the coring tube. That's okay. We don't have to collect all of it. But you extract the coring tubes. The spacecraft has legs, so it then walks a few centimeters, and it repeats the process. And it keeps doing one set of coring tube extraction operations after another until the tank is full of water. Every time it'll shove that tube down in the icy regolith, it'll get some of the vapor out, and it'll pull the tube back out again. So you can actually get the ice out of the dirt. On the other hand, on a third example, if you're on a carbonaceous asteroid, let's say
carbonaceous, that's an awesome word.
So carbonaceous those are the asteroids that have a lot of clay in them.
Okay.
So Ceres, the largest asteroid, is a carbonaceous asteroid, for one example. So if you're on a carbonaceous asteroid, there is no ice. Instead, the water is actually locked into the mineral structure of the clay itself. In that case, you can still get the water out. You drive the coring tube down into the soil. You heat the soil so much that the hydroxyl that's in the clay starts to break loose, and it comes out in the form of water. So you still can get water even on a bone-dry asteroid.
Man, this is like blown my mind, Phil. This is awesome. So obviously, if you're harvesting in frozen deposits of water or water mixed into regolith, we're in fairly cold environments. Is this robot able to survive in these really like harsh environments?
Sure. That was part of the calculation, how much energy it needs to stay warm. And there's a lot of different ways to do it. One way is you simply try to stay in a benign environment. So there are places in the solar system where it's not so cold, and you design it to handle the average temperature. But if you want to go into a really, really cold place like Pluto, then you're going to have some warmth on the spacecraft. And the way that we do that in the space program is we use RHUs, radioisotopic heater units. Each RHU is the size of a dime. And you just simply glue them onto your spacecraft at various locations. They contain a tiny amount of a radioactive material, and over time that material decays and creates warmth that goes into your spacecraft.
So you're using radioactive dimes to heat a spacecraft to keep it from freezing.
Yeah, that's actually standard practice. We didn't invent that. But so to go to these colder areas, you would have to do something to keep them warm in order to keep the electronics functional.
And we talked about the way this thing gets around and how it kind of gathers its propulsive materials, but I'm assuming that this robot is for more than just hopping around. It's got to have some kind of a function that's scientifically beneficial.
That's right. It would carry a payload. And one of the nice things about it is that the spacecraft is already mining the volatiles. So if you want to study the volatiles, you've already got access to them. So you could put some instruments on your spacecraft and you could study the chemistry of the volatiles. You could study what temperatures the volatiles are released from the soil. And that gives you information about the clay minerals and the physical state of the ice in the soil. You also could carry a camera. Obviously, you will have a camera because you need visual awareness as you're hopping and landing. Sure. So you'll get visual imagery of the body that you're exploring, but there's also accommodation for other payloads. So you could take magnetometers, or you could take spectrometers, or anything else to study the mineralogy or the planetary environment wherever you go.
What are some of the major challenges that lie ahead for you all? Obviously, the goal here is that this will be operational and exploring somewhere in our solar system, but what are the big speed bumps to getting there?
Yeah, it's a matter of doing the engineering. So NASA has a way of grading technology. It's called the Technologiness Readiness Level Scale. Did I say that right?
I think that sounds right.
Technology readiness level.
Yeah.
And so it goes from 1 through 9. 1 means you've discovered something in physics.
Okay.
2 means you've come up with a way to use it in technology. And then it goes all the way up to 9, which means you're now flying it in space.
Okay.
So we are at TRL 4 or partial TRL 5.
Okay.
Because we've built a partial prototype. And we have tested it in a terrestrial environment using a gravity offloader, but using realistic regolith and vacuum. So it was partially the realistic environment and a partial prototype. So in order to get a full TRL-5, we would need the full prototype with all the spacecraft systems, I think. And then in a full relevant environment for the testing, so maybe some testing in space actually, to get TRL-6. And once you're at TRL-6, that's the point where you can sell it to your customer. Then the customer's job is to build the actual flight units to go 7, 8, and 9.
And for you, as you kind of look towards the future, obviously it sounds like a customer gets involved, so they kind of have some say in this. But do you have to go further than the moon to be able to test this, or is the moon an acceptable testing ground for you guys?
Well, to get TRL-6, you don't actually have to go to space. You can simulate it, but you have to put together the full set of relevant space conditions.
Okay.
So we have tested in vacuum. We used a gravity offloader, but we would probably want to test the mining process itself, the coring, in a reduced gravity flight. And we would probably also need to have the right thermal environment on the spacecraft. So not just a vacuum chamber, but a thermal vacuum chamber for some of these tests. Once we've done all that, we could probably claim TRL-6.
Cool. Any words of advice that you would give to aspiring planetary research scientists, or possibly something that you might say to inspire people to be planetary research scientists?
Well, I'm having the time of my life. This is exciting. It's fun. I do something different every day. I'm working on about 5 or 6 different projects at all times. So there's a lot of variety. And you get to make everything up as you go along. So if you like, I mean, there's no book that tells you what to do next. What we're doing is we're creating an off-world economy. So I call myself an applied planetary scientist.
Okay.
Or I'm doing economic planetary science, because we're working on the technologies to do economic activities off the Earth. This is not an established field, and so we're making it all up as we go along. This is also what the SwampWorks does at the Kennedy Space Center. The SwampWorks, in my opinion, is the premier laboratory for space mining and space resource utilization in the world. And some of the best technologists in the world are here in NASA doing this work. When I was at NASA as part of the SwampWorks, we were making it up as we go along. We're trying to figure out, we're inventing technologies, we're inventing processes, we're inventing strategies and entire space architectures. And then we convince people to give us the money to do it. And then we get to have fun, and we go work on volcanoes, we fly in reduced gravity airplanes, and pretty much anything you want to do. We're working with real rockets, and with robots, so robots, rockets, and we're doing things to help humanity. So it's kind of the best of everything.
All right, I'm ready to go. Sign me up. I'm in.
All right.
So there you go. So as we look towards colonizing the moon or Mars or other heavenly bodies, Phil Metzger is a brilliant man who has lots of data to share and obviously lots of energy to do so. So thank you for being with me today.
Thank you, Josh.
As promised, we wanted to answer a question from a listener. Cassashine asks, what is the most exciting thing to look forward to regarding SpaceX and private companies also being about to travel to outer space? So you may or may not know, but part of NASA's mission is to expand commercial space. So for any company that gets into that game of taking humans into space, that's a huge win for NASA. And we really see that as a benefit for all mankind, because the more companies that enter the field, the more competition there is. And so that actually will drive costs down and make commercial space more accessible for most people. So over time, the cost of flying into space will take a huge plummet. And that's awesome, because then everyone will get a chance to hopefully someday vacation in space, visit the moon, or even further than that. So we're excited for all these commercial companies and a growing field. Mike, we had a chance to sit down with Dr. Phil Metzger and talk about the WINE project. Is this an exceptional project, or is this par for the course when it comes to SBIR and STTR?
It's a great question because the SBIR program has been responsible for bringing forward a lot of really amazing companies and teams doing remarkable projects. So we're lucky to say that, yeah, there are quite a few like this wine project that really knock it out of the park. And it's hats off to the small businesses that put all the effort in for this program, that's for sure.
So you mentioned that we're looking for research projects that we could see some commercial application. Is that a priority for us? Are we really helping to kind of like kickstart these commercial deliverables or products, or however you want to describe it?
We try in general to make sure that the company's participation in the SBIR program is something that's going to benefit them in the commercial world as well as the government world. And there's a couple different ways how that happens and why we would want it to happen. It helps in the commercial world in the sense that we're interested in making sure that these small businesses are functional and available to us for future use as suppliers. So a good way of saying it for the SBIR program, and in fact, this kind of leans towards it, a good way of looking at the SBIR program is for NASA, we're trying to build pockets of the industry that we know we're going to need in the near future. So while we know that there's suppliers of prime contractors and established suppliers of different types of technology, if we can see that a few years down the road, we're going to need some new category or class of sensors or what have you, it's worth it for us to put some seed money out through the SBIR program, work with small businesses, and collaboratively try to develop that little niche in the industry and see if we can grow it.
Can you talk about kind of the process? So whether it be for wine or for any SBIR, I would assume the process is similar. Kind of what do they go through from a NASA perspective to develop this technology and get it ready for flight?
Sure. The NASA SBIR process is actually something that has a couple different phases. The first part is a phase one where we send out the solicitation to the general public and to industry, and any company or any person who's starting a company even can apply. And they're applying for a phase one award, which is $125,000 for 6 months or 13 months worth of work, depending on whether it's the SBIR program or STTR program. But that phase one, what that's basically doing is what NASA's asking for, I should say, is something of a technology development plan. You think you have an idea. How would you develop the idea if you had funds, and what kind of preliminary work can you do up front to validate or better plan for it or even disprove the concept? That's kind of what the phase one work does. And then what happens is at the end of the phase one period, the company submits a final report, and they're also invited to apply for phase two. So you don't get to phase two unless you've been awarded a phase one.
Okay. And
the phase two is sort of follow-on work. So that's the second stage of the work. The nice thing about phase twos is it's a bit more time. It's 2 years worth of duration, and it's also $750,000. So between those two, you're close to $1 million worth of funding that NASA has provided to the small business to pursue that particular technology. So the World Is Not Enough project, the wine project, has proceeded through phase two and has gotten to where they've been able to develop hardware. And that's the exciting part about the phase two project. By the end of phase two, NASA is generally expecting to see some sort of hardware that will be delivered, or a software prototype, something like that, some sort of proof of the technology. And between those different phases, it pretty systematically helps bring the companies up in terms of developing their technology up through the technology readiness levels.
Mike, the STTR program being different in that it incorporates universities. And I think there's part of me that's continuously impressed by the fact that we do have university students really contributing to NASA missions. Can you talk about the value of those students? Like, is it more learning for them, or is it more value for us?
The approach that has really worked well in the past, and I think is the reason why the STTR program was structured the way it is that not only do you need to find groups of people who are capable of coming up with innovative solutions, but you also need to think of it more like a process. Where do these people come from, and if they're going to grow into big companies, how do you supply them with people who have familiarity in those fields? But also, you're not just growing companies, you're growing whole areas of thought and development. And a lot of times the academic world is critical for that. At NASA, we pay a lot of attention to technology ecosystems, as I would call it, where the different elements that are needed in a particular region in order to support technology development, it's very hard for a small business by itself to really be able to thrive in some of these demanding worlds if you don't have some kind of support. And a lot of times the nearest university or research institute can be just the critical lifeline that a small business would need. And we want to try to encourage that. That's part of why we have the STTR program. We found it to be extremely powerful for small businesses to make an effort to reach out and interact with universities, particularly if they're doing technology development, because it is the exchange of ideas that is pretty staggering. And small businesses also don't realize that sometimes there are more opportunities than just our STTR program that require a combined team. And it's a real vibrant part of the research world, and there's nothing but benefit to get if people can team up like that.
All right, Mike, that's all the time we have for today. Thank you so much for being here. I'm incredibly excited. Obviously, an exciting time for SBIR as we look to return to the moon. Thanks for joining me.
Thank you.
I'm Joshua Santora, and that's our show. Thanks for stopping by the Rocket Ranch. And special thanks to our guests, Mike Vinge and Dr. Phil Metzger. To learn more about SBIR and STTR, visit sbir.nasa.gov. To learn more about how NASA technology benefits life on Earth, check out the 2019 NASA Spinoff magazine, which is out now at spinoff.nasa.gov. And to learn more about everything going on at the Kennedy Space Center, go to nasa.gov/Kennedy. Check out NASA's other podcasts to learn more about what's happening at all of our centers at nasa.gov/podcasts. A special shout out to our producer, John Sackman, our soundman, Lauren Maythree, editor, Michelle Stone, and our production manager, Lee J. Lockhart. And remember, on the Rocket Ranch, even the sky isn't the limit.